Hi, I'm Jennifer Morrissey, Executive Director of the Mission Trails Regional Park Foundation. Welcome to the first installment of our Mother Nature in San Diego series. Before we get started, I'd like to introduce some of you to the Mission Trails Regional Park Foundation. We were founded in 1988 to help preserve, protect, and enhance mission trails. Our support of the park is broad and ranges from purchasing plants for habitat restoration to helping to fund major projects such as the construction of the Visitor Center and the new Ranger Station, which opened last year. The foundation also provides significant funding for field trips and education programs. As you consider your charitable giving, we hope that you'll make a gift to support the park and the foundation. Tonight, we would like to thank two special supporters of the Mother Nature in San Diego series, our longtime educational partner, SDG&E, and the Samuel I. and John Henry Fox Foundation. We hope that you will join us for the other lectures in this series, which will focus on earthquakes, floods, and wildfires, and consider how natural events have impacted and could affect the San Diego region. Thank you for attending, and many thanks to Dr. Abbott for presenting this series.
Hello, I'm glad we have a chance to talk about climate here this time. You know, climate is such a fascinating topic. And you know, when we add the fourth dimension to time, as we geologists do, it becomes even more fascinating because we learn more lessons from past climates. And that's kind of what I thought we would do here this time is drop back and look at things millions of years ago, thousands of years ago, come in at different time frames to give us different views. The concept being learn something from each of them and hope we put together a smorgasbord of new concepts or new ideas. Now, the first thing, breaking news, the very first thing here I got to do is this year's Nobel Prize for Physics was basically awarded to a climate modeler. As it turns out, simply modeling incoming sunshine, the water vapor, the very potent greenhouse gas, and carbon dioxide allowed computer modeler to model thousands of numbers where each number can affect other numbers and still come out with a viable climate model. In fact, in 1970, when he first published this, his temperature, he was only 1 degree off on predicting that temperature for 3 decades later. So this is a huge, huge step for all of us. It basically means that a lot of that scientific information that we've been getting for all these years, when we look at these changes here, like take an average temperature for 40 years and then compare above or below. And if you start up in the upper left there, 1979, you see temperatures are below the long-term average. And as you read it like a book all the way down to 2018, what do you see? You see that global warming. You know, and it's interesting because Dr. Manabe, who was awarded the Nobel Prize, he basically has known this or figured this out 50 years ago. That basically means that 50 years worth of warnings we've had and lectures about here's what's coming, despite all the naysayers and doubts, they were quite correct. And it makes me think a little bit about the philosopher Arthur Schopenhauer from 200 years ago in terms of how long does it take or what does it take for people to get a hold of some idea. And here's his 3 stages. And try this on the climate thing. At first it's ridiculed. Can you affect the climate yourself? How can that be? And then the violent oppositions of, you're going to destroy the economy, you're going to do this, and so forth. And now finally we recognize that it is real. Now, you know, if I could, as a geologist, just one other example of Schopenhauer's 3 stages towards truth. When I was a young student just learning geology, that's when some of the first ideas about plate tectonics started coming out. And at first, most of the professors I had were ridiculing them. There were some violently opposed. This sounds extreme, but one of the professors, this was a major factor in him going for early retirement. His worldview was being changed so much, he just didn't even like it. He wanted to get out. And now, where are we? Years later. Students learn about it in elementary school, middle school, high school. We now understand plate tectonics is one of the ways the Earth works. But we still went through all those stages to get to that point. Now, that's the breaking news. That's now. Let's go back here and look at some things here about ancient climates. And I thought I might focus a lot of this on ice ages. It turns out, well, let's look at the next slide and get some idea about this here. Now, what I'd like you to see here is if we start way over here on the left, 500 million years ago, and as we work our way over towards the right up to today, there's climate in the last 12% of Earth history. Now come up the vertical axis over on the left, and there's average Earth temperature ranging from 50 to 90. Just for orientation, or at the present time, the average temperature of the Earth is 61 degrees. We're below that yellow line. Now, what I'm after here is as we follow that line, red being too hot to have an ice age, to have continents buried beneath ice, or we go below the yellow line there, and those blue times, those are times when the Earth is cold enough that you could support an ice age. And where I'd really like to start is right here in the center. Here, look here, 360 million years ago, 300 million years ago. Look how long that ice age lasted, tens of millions of years. So what we're looking at here for something tens of millions of years, we have to have slow-acting, long-term processes. And the big setting for this is plate tectonics. Where are the continents and how are they situated? Because they in turn affect ocean circulation and the distribution of heat, of energy, of the climate. But the other big thing during this time there, at 360 million years ago, that's when plants started coming out of the oceans and spread across all the continents. So for tens of millions of years, you had massive forests, ferns, rushes, plants pulling carbon dioxide out of the atmosphere so much that they helped drive the Earth into an ice age. And you know, I like to pause a second and think about that. You know, we think about, well, climate affects us, climate affects life, but it's a two-way street. Life also affects climate. And we're here 350 million years ago, 300 million years ago. Life is pulling so much carbon dioxide out of the atmosphere, it put the Earth into enough of a freezer to have a long-term ice age. And then, of course, now when we think about it, what are we doing today? We're digging up that coal, burning it for energy, and returning that carbon dioxide back to the atmosphere that the plants pulled out 350 million years ago. So that's a take-home message right there. Life and climate are inextricably linked. Each affects the other. Now, let's move on over to the right-hand side of this here in the today part. Look at this. Look where we are there. When you're looking there, you see that about 34 million years ago, Earth cooled off to the point that we get another ice age. And the first part of the blue lines you see there, the upper part, that's Antarctica getting covered with ice. But when we look farther over and where the line drops down, that's when the northern hemisphere starts being buried in ice as well. So did you ever think of it that way? Did you think you're living at one of the colder times in Earth history, an ice age? I know when I started in elementary school, you learn things about how the Earth is set up. You know, here are the oceans, the mountains, the rivers, the continents. You learn all these things. And then they say one of the continents is buried beneath ice, and the largest island on Earth is buried beneath ice, and that's the way the world is. No, that's not the way the world is. Looking again at that graph, it's an unusual time when you have whole continents buried beneath ice. So we are alive at a cold time, and yet we're warming it up away from our comfort zone. As we change our view from millions of years to thousands of years, what I'd like you to notice again down here on the bottom, here's the time frame where we're a million years ago on up to today. And then the vertical part here with the red lines, the higher the red lines, the greater the advance of the glaciers. What we're working on now is not whether we have an ice age, but when you have an ice age, like we're living in, the glaciers aren't static, they advance and they retreat. And so if you look at the peaks, each of those red peaks, can you count the peaks across in the last 900,000 years and more or less see 9 peaks? On roughly every 100,000 years, we've had the glaciers advance significantly, and then they pull back. And an interesting thing about that, when you look at how it goes here, let's look at the latest one over on the right-hand side. You see that the glaciers advance very slowly for tens of thousands of years, and as we will see, they drop rapidly in a matter of a few thousand years. A tremendous asymmetry here. But we want to go on now and look primarily at what I'm going to call the causes for why the glaciers advance and retreat, and those have to do with the Earth's sunshine, how much we get. At the top there, eccentricity. Again, go to the bottom here first, if you would, and look at that time scale. Down there is 250,000 on the left, on across all the way to 100,000 in the future. And by eccentricity, we're saying that the Earth doesn't just go around the sun in a circle. Its path varies. And the farther away it is, the less solar energy we receive. And then the tilt of the Earth's axis. If we look at the tilt of the Earth's axis, if you, for example, here on full screen, if you are the sun and the Earth's spin axis tilts towards you, there's going to be more melting of snow. The higher the tilt axis is, the less solar energy is received. Now, when we talk about this advance and retreat of glaciers, what we're really just doing is magnifying the individual year. Every year, snow falls and builds up. Every summer, snow melts and melts back down. So the trick here is, what's the result of a year? Did you end up with excess snow? Now multiply that times thousands of years, and you're building an ice sheet. If in the summer you melt back down and the snow's gone, then we're at a time without glaciation. We, of course, are here in the middle of a time of glaciation. And I want to move now and kind of focus what I'm going to call more our time. To a geologist, 20,000 years, this is basically historic time. You think 20,000 years ago, think about the population in Europe, think about the population in Asia, Indonesia, the Philippines. There's lots of people living through these exact conditions that we're going to look at of what happens in the last 20,000 years. And 20,000 years ago, that was the peak of the last glacier advance. We refer to it as the last glacial maximum. So what we're going to do now is start entering into this world that we live in. Now, in this view here, you see North Pole right in the center there. This is 20,000 years ago. And you look around, well, if we go around it clockwise from where it says North Pole, there in the upper left, there's ice sheets covering Russia, Siberia. You come around clockwise, there's Greenland beneath ice. There's Canada, New England, portion of the United States come across North America. And you see a very icy North Polar region. And then the oceans there are covered with ice as well. Now, what has happened then since that 20,000 years? Of course, when we look at it and just focus on North America, I wanted to talk about this diagram because when you look at it and you see 20,000 years ago, this schematic sketch here of what North America looked like buried beneath ice, I think when you see that picture, you tend to think about, oh, well, during that time, snow is just falling throughout all of Canada. And as the snow falls, it ends up burying Canada. Less screen, please. So the snow falling all over Canada picture is not correct. What actually happens, it starts over on one edge, the snow builds up there so high that the ice, which is a weak solid, can't support itself, and then it flows out like a giant bulldozer covering Canada and coming down across the Great Lakes into the United States. Now, I'm going to demonstrate that for you here in just a little bit, but basically, the snow doesn't just form in one place, the ice doesn't form in one place. It tends to form in spots and then move out from those spots. Now, if we look here at ocean water circulation, focus, if you would, on right in the center there at the Atlantic Ocean. And what I'd like you to notice here is something that's familiar to you. Along the east coast of the United States and Canada there, we have the Florida Current, the Gulf Stream, taking warm water up northward. And that's the key to building the glacier that buries Canada. It takes warm water to be evaporated to create lots of snow. If it's cold ocean water, you don't evaporate much. So what we're saying here then is that the snow falls on Labrador, Newfoundland, those areas, and then spreads out across North America. Now, I still haven't demonstrated that yet. I'm giving you the explanation, but I haven't shown you why we can say something like this. So let me look next here. Here's a picture from John Shelton, one of the great geologist photographers of all time. And what's he showing here is rock that has just been scoured over by glaciers. You can see the grooves and the scratches of the ice going over it. Now, what we can measure is how long a rock surface has been exposed. Let me back up. When ice is covering the land, if we can see that, ice is covering the land. Less screen, please. Then the ice absorbs all the solar Then when we have a lot of ice, it absorbs the solar particles coming in. But by the time ice melts, pulls away, and rock is exposed, now those solar particles are coming in, hitting the surface, and burying themselves in the rock. Let me give you an example. Beryllium atoms being thrown out from the sun. Beryllium-10 is radioactive, beryllium-9 is not. We can start to measure this and other isotopes like aluminum-26, and we can tell how long a rock surface has been exposed by the buildup of solar particles that have bombarded it. So what we're measuring then is not the ice, but the absence of the ice. What we want are rock surfaces like you see here in John Shelton's image, and then we can tell how long that surface has been exposed. If we go to this next map, this is where we're going to see the whole thing here now. What I want you to notice here are those numbers in white. They represent thousands of years. So let's go down to the bottom of the diagram here in the Great Lakes area. You see that 18,000, 14,000 numbers there. That's saying that the rocks there were exposed, became exposed 18,000 years ago. In other words, the ice sheet pulled back. Now follow that northward or up the screen, you come all the way up to see where it just says 6,000 years ago. In other words, we're up to the spot from where the snow fell originally, built up the ice mass, and then you can see in the different colors of blue how it spread out and covered the different parts of North America at different times. So the whole glacier story is, well, I think a lot of that maybe is not intuitive, but it is kind of fascinating. If we want to see if we're going to enter another ice age here, another glacial advance, we would start looking up there in that Labrador area first and start saying, oh, look, the ice is building up here. That would be the start of another big glacial advance. Now the numbers, I don't want you to get caught up in all these numbers, but if you look at the top label there, Eastern Canada, how much ice melted in that 20,000 years? Over here where it says, in the upper right where it says sea level rise, 70 meters. That's like 220 feet of sea level rise from the melting of the ice on Canada. And look at the other big numbers. You go down that sea rise column, down there where it says 30 feet, read over, that's Europe and Siberia. So what we're seeing is Antarctica, not that much ice melted. We're seeing it was mainly in Siberia and Eastern Canada. And going back to what we were talking about, the snow, the ice buildup was in relatively small areas. Now, let's pause a second and think about this. If we're going to bury the continents with ice miles thick, where do we get all that water to make the snow? It's got to come out of the oceans. And to pull this much ice, this much snow out of the water out of the oceans, sea level has got to drop. And now we're going to get into things that really affect human beings. Here is a sea level curve, and I'll describe it to you in a moment how we know this. But look down in the lower left, if you will, over here. So there's thousands of years again. See where it says 24 and 22? That'd be 24,000 years ago. And there's sea level. Now, if you come all the way over to the right, that's in meters. So we're talking about something at 125. We're talking about, say, 415 feet. Now, think about that. 415 feet lowering of sea level. Imagine what that does to Europe, to Asia, to any point in the world. And now look at the sea level rise curve. That's what we're talking about here, is the rise. And when you see that rise, it's very, very sharp. They're starting about 14,000 years ago, going up to about 7,000 years. Tremendously rapid rise in sea level. In 7,000 years, we had sea level come up over 400 feet. And now at the present time, you see it's still rising, but nowhere near the rate it rose at that time. Now let me tell you how we know this. See all those little different colored of X's and the descriptions over there on the right? Those are dates that are measured on coral reefs. Think of the Great Barrier Reef off of Australia. Well, that forms basically at sea level. When we find ones, like off of these various places that are flooded at great depths, then we can measure the age, uranium, thorium, isotopic ages. We can measure the age of when that was a living coral reef, and then it can tell us how much sea level has risen by the change from when it was alive to how deeply it's flooded beneath the oceans now. So what do we see here? Relatively little change in sea level, rapid change, geologically speaking, 400 feet in 7,000 years. That's affecting a lot of civilizations of their time, and then we level out again. Little cartoon here. Up near the top, the blue line running from left to right with the arrows pointing at it, there's how far the glaciers had advanced 20,000 years ago. The Great Lakes states, New England, New York, covered beneath glacial ice. Then the red line running along the right-hand side and the bottom of the diagram, that would be where the shoreline was at that time. So at the top of the map, we lose the great states and New England, but on the other hand, look what happens to the East Coast. Look at Florida, my goodness gracious. Look what a huge state that's become, and for that matter, the other Gulf states there, Alabama, Mississippi, Louisiana. So part of what I'm talking about here is recognizing sea level changes on this thousands of years interval. These aren't our times. This isn't something we're going to see in our lifetime, but these are the kinds of changes that can happen or are in the early stages of happening. In other words, what kind of a world are we delivering forward for thousands of years? Now, I put this diagram on it because I wanted to talk about, just for what we feel, how small a change of temperature can actually affect day-to-day life. So if you look over on the left-hand side here, you see 1.5 C, 1.5 degrees centigrade, or say 2.7 degrees Fahrenheit. And then you look at the red line up there, medieval maximum. So where are we here? We're at the year 900. We're coming up to the year 1300. Medieval maximum, a time very, very warm. And then the red line drops there around the year 1400. They called the Little Ice Age. The glaciers in Europe started advancing again, moving down the mountain valleys, out onto the plains, running over some towns, forcing them to move. And then we have the Maunder minimum, which means the sun spots. There weren't any for years and years. The sun put out less energy than it normally does, and look at the temperature drop there again. And so then you see the rise as we head up into the 20th century. So I'm just trying to give you a little effect there that even slight changes in temperature are things that can affect our day-to-day lives. These aren't crippling changes, but nonetheless, even slight changes add up. And of course, what we feel, we can handle those temperature changes better, you and me, but agriculture, things like that, plant production, food production, those things suffer far more. And here's this, what they call the hockey stick, trying to average out all the readings for the past 1,000 years about the Earth's temperature. And you see a lot of fluctuation, but the stunning thing is, when you come up to our times, look all of a sudden here, on the right-hand edge, how steep it gets, how hot things have gotten here in this last 150 years or so. I'd like to go up to the Arctic, if we can, and look at a few concepts here. So when we're looking at the Arctic here right now, when you look down in the lower left, you'll recognize the outline of Greenland, and the main center of the picture there is the Arctic Ocean covered with ice. And if we pull back a little bit and look at it and say there's Greenland near the top center, pure white from the light reflecting off of that snow, and then the arrow pointing at the gray, which is the sea ice covering the Arctic Ocean. And what we're talking about here was that fabled search for the Northwest Passage, where the European explorers got busy there in the late 1400s, 1500s, 16, 17, 18, 19, going through all those centuries trying to get through there. They never could because that ice always blocked them. The Northwest Passage was unattainable. Now look at a photograph from 2011. What was unattainable for centuries, now look at the northern route along Russia, an arc there, how easy it is to run ships through there. Or in the southern route, winding through the ice off of Canada, you take a little more seamanship to get through there. But the Arctic Ocean is now open several months of the year to the largest seagoing tankers we see. And I bring it up here right now partly because I can't think of hardly any better evidence for global warming. An ocean that was covered with ice for centuries is now open during part of the year. And I want to discuss another thing here. This word albedo, it's basically reflectance. So sunlight coming in, hitting a white surface. You've all had that experience probably, right? You've been out on the snow someplace and it may be freezing weather, but the sun glaring or reflecting off of that snow is blinding to you. You're wearing sunglasses even though the air is freezing because incoming sunlight is reflected by the ice. But what happens to that water that you see exposed on the left-hand side of the Arctic Ocean? The sunlight that comes in there is heating the water. So every year now we're adding more heat into the Arctic Ocean. The more heat we put in the ocean, the less ice is going to be able to form the following year or following years. And when we start to look at these things, this is from satellites. We've had good satellites going over the Arctic Ocean since 1979. You notice along the bottom axis there, we're starting in the year 1979, and we're coming up through the year our year, 2021 here. And if you look at if you forget the numbers over there about ice volume, just know it was a lot bigger. And if we look at the decline in ice volume now, I'm not talking about the area you see in the photo, but also the thickness of that ice. Because the ice there used to be ice down here that was tens of years old, 15 years old, 10 years old. But we now have this incredible thinning of the ice. And most of the older ice is gone. It's just thinner, younger ice. And you look here at the minimum part. Look at that. On the left, in 1979, it was 17,000 cubic kilometers. Now look at it at this year. We're down below 5,000. We're on our way out for seeing year-round or extensive sea ice covers of the Arctic Ocean. As the Arctic Ocean absorbs more heat, as it becomes warmer, it's going to have tremendous ripple-down effects throughout the world. Which brings up this concept of tipping points. And I know this is something that's been around a long time. It's not a brand new term for anybody, but I consider it to be one of the most valuable concepts around. Tipping points. We're seeing changes, but how long can you get away with a change until a tipping point comes from which there's no return? And the tricky thing with tricky points is you can't see them in advance. We don't seem to be able to see a tipping point until you've gone past it. And let me go a little bit farther with this here. This is a crude diagram. I don't have the finished one, but this is what I sent into my publisher, McGraw-Hill. That's just my scratchings there of trying to identify some tipping points, possible tipping points throughout the world, things to look at, changes that could be coming. And let's just focus in, say, a few up on the north there. The Arctic sea ice melt we were just talking about, but the stability of the Greenland ice sheet, talk about deep water circulation in the North Atlantic, and talk about global sea level rise. Let's go on and talk a little bit about each of those, just as examples of tipping points that may be approaching and what's liable to happen to the Earth if we pass those tipping points. So, methane bursts. You know, methane is a gas, well, our best calculation right now is that of the global warming we've been experiencing in recent decades, about 16% of that is due to methane in the air. Methane is 1 carbon, 4 hydrogens, CH4. The methane, that's the main component of natural gas. It's a very powerful gas. Say, in a 20-year period of being released into the atmosphere, it would be about 80 times more powerful than CO2. But the good news is it doesn't stay in the air as long and is removed sooner. But this is one of the things that's definitely adding to global warming. Now, what I want to do here is look at spectacular examples of methane release. We're in Siberia here, and this is an explosion. This is 165 feet across. It's deeper than a 16-story building. And what do we have in Siberia and Canada? Well, let's talk about the Northern Hemisphere a moment. About 15% of the Northern Hemisphere land has permafrost. And permafrost means there's ice in the soil below the ground surface that's there year-round. And what that means is, in all that permafrost, since the glaciers retreated there, we saw that the various thousands of years ago it retreated off of Canada and Siberia. That means vegetation that has died, a lot of it has been preserved by the ice. So we have hundreds and even thousands of years of dead vegetation preserved in the permafrost. Now that things are warming, permafrost starts thawing, some of that methane is seeping out, and in some places like here in Siberia, here's the ground surface, and there's ice down beneath it that's made a cap that's holding the methane under it. But as that ice melts, some of that methane comes up, accumulates in a big enough blast. Well, it's kind of like what you see in the news at times when you see a picture of a house that blew up in some neighborhood. Well, here we're talking about a much bigger blowout. Imagine that hole formed in a matter of seconds. That is a horrendous blast of methane. Now, I'm focusing on the spectacular blast right now, but talking about climate, what are we talking about? Loading large amounts more of methane into the ground surface. And we look around Siberia, here's one I'm ready to go. They've counted over 7,000 of them, and doesn't that kind of look like a loaf of bread out of the bakery or something? But what is bulging up the ground there? The ground is bulging up because of the methane that's accumulating below it. And this, you could visualize this much like a volcano. Instead of it being magma buoying up the surface, it's methane gas, and that can be released in these huge explosions like we just saw the result of. I want to talk about Greenland some more. You know, it's interesting when we had this looking at the North Polar region before, I reoriented that to kind of put Greenland in the center there a little bit. But what I want to do was 20,000 years ago. And now 20,000 years ago, to a geologist, how long is 20,000 years? That's a short amount of time. We're basically in historic kinds of times. Now, all that ice is gone, and if we look at that same thing now, what do we see? The ice is gone off of North America. It's gone off of Siberia, gone off of Europe, gone off of Scandinavia, and we have one piece left on Iceland. How liable is that to go? Well, the middle of the picture is the Arctic Ocean, and we've just been talking about how the Arctic Ocean, being freed of ice, is absorbing more sunlight, and the water there is getting warmer and warmer. So what happens when the Greenland ice sheet melts? Where's its tipping point? We don't know. But, you know, in class what I like to do is I like to bring in ice cubes and put them on the counter, and I like to say, this ice cubes have had their tipping point passed. They're out of the freezer now. The room temperature means they're going to thaw, they're going to melt. But they don't melt in an instant, do they? It takes quite a while for them to actually melt and turn into liquid water. And then, of course, in class, I say, well, how can we stop this? And I always get some help from the students about, well, put them back in the freezer. Yes, that'll stop the thawing ice cubes. But when Greenland passes the tipping point and starts melting, how do we reverse it? It's irreversible once it starts, unless Mother Nature steps in somehow. So let's look a little bit here about, let's melt the ice on Greenland, and what do we see? Well, here's Florida. There's an 8-meter rise in sea level. The red area of Florida, wow, it's what, about half the size it was? Look it up there in the upper right, along all the New England area right there, all those major cities we have right there along the coastal areas now flooded. Come on over and, wow, look how much of Louisiana is lost. Or let's come closer to home. What happens if Greenland melts? Well, no Mission Beach, no Lindbergh Field Airport, no Coronado, no downtown, no San Diego Bay. Oh, but we do have, well, look, though, we do have an island. We could call that island Loma, but it's a radically different to civilization melting Greenland than what we're used to living in here now at this time. Now, here's another one, a little more esoteric, the North Atlantic Deep Water Formation, but I want to just mention this a little bit. This is from Wally Broker. It's a very simplified diagram of ocean water circulation. If you want to say it this way, a drop of water would take about 1,600 years to complete that whole circuit. But what I want to call your attention to right now is this part way up here, up near Iceland, Greenland, where it's deep blue colored. The deep blue is cold water that's sinking, and then you see that cold water flows all around the world oceans. So one of our concerns now is, as the water over here warms up, does it warm up so much that it doesn't sink? If we don't have cold water sinking up near Greenland and Iceland, then we're not stirring the whole world ocean. The world ocean can become more stagnant and warmer and be a very different world than we're used to. So what we're concerned with then is just that. Can we still have cold water sink and flow through the deep oceans, or are we going to warm up to the place where that won't work? Another concept I wanted to bring up here is lag times. We're talking about melting of Greenland ice. It doesn't happen real fast. But let me do this one. Here's one that's kind of hard to wrap your mind around a little bit, or at least I had a hard time with it at first. But let's just say that you had a glass of sparkling water or 7-Up or champagne or whatever with all those carbon dioxide bubbles in it. And when you're releasing that carbon dioxide into the atmosphere and it absorbs into cold water and is taken into the ocean water, what's that effect on future generations? Not quantitatively a lot if it's just your glass of water, but that cold water with that carbon dioxide in it's going to spend over 1,000 years circulating in the deeps before it comes back up again. In fact, more of the carbon dioxide we put in the atmosphere these days is absorbed into the oceans than stays in the atmosphere. So basically, we are mailing forward to future generations a much warmer ocean than we have lived with. I just wanted to, a couple, maybe 3 more diagrams here looking at some of the modern. I wanted to look here at, here's going from 1880 up until the modern days here, looking at warming of land and ocean. So you'll see the black squares, that would be the year's temperature. The red line would be a 5-year average running through it. And we see that the global warming is not just a straight line event. You look here early, 1880 up to 1920 or so, it's more or less revolving around one spot. But we go from the 20s up until the 1940s, and it warmed up much more rapidly. And it's been suggested that the sun may have been putting out more energy at that time for that warming. But then we go through the World War II area all the way up into the 1970s, no real change. And then we've taken off with the one that's in the news all the time, the global warming that everybody talks about and even gets political about. And did you notice here that early on, in the early part there, 2000 and across, it leveled out again? And you remember the anti-science people then saying, oh, global warming has stopped, it's all over, there's no more global warming. Well, even when they're saying that, if you look at the individual black squares, they're still the warmest years we ever had. And we now have that one kind of figured out about what happened at that time. We had a huge pool of cold water in the North Pacific Ocean. And what we think has happened was that cold water at the surface for all those years caused more carbon dioxide to dissolve in that cold water, so not as much of it stayed in the atmosphere. But since those few years, well, here's the story since. We're racing on out of control. We had a brief reprieve here with last year, pandemic year, but we've already erased most of that, and CO2 is going into the atmosphere at a faster rate than it ever has. And here's those CO2 measurements from Charles Keating out here at Scripps, beginning in 1959. And look at the CO2 content there. We start out at about 315, and we run up to now, we're about 415. That's the carbon dioxide just being pumped into the atmosphere year after year. And I want to bring up my last point here is the thing that is least talked about cause behind climate warming. The topic most people are afraid to handle, and that is the growth of the human population. To talk about human population, you can offend people on nationalistic grounds, religious grounds, anything you can think of they can get offended about. But what I want you to notice here is follow these curves up. Notice here that in 1922, near the lower middle part of the diagram, that's when the Earth reached 2 billion population. 37 years later, in 1959, we reached 3 billion. In 15 years, in 1974, 4 billion. I count them up, 5, 6 billion in 1999, 10 billion 2011. We're on our way to 12 billion. And notice the years between those, 12 years between, 13 years between. And that means that every 12 years, the population of human beings on the Earth is growing by 1 billion people. And by growing, I mean we've already subtracted all the deaths, wars, disease, old age, you name it. Subtract all deaths for whatever region, compare that to births, and what's the net? The net is that we gain 1 billion people every 12 years or so. And those 1 billion people, all of them, whether they're rich or poor, all of them being alive, add to global warming. And for those that are poor, they would want to be rich. And for them to become rich, which I'm not opposed to philosophically, but I'm just talking about climatically, if they all become to live the exact same way we do, the Earth will become, well, incredibly hot. So there we are. We kind of see these things. And when I plot the human population in a real scale, no logarithms to smooth it out, it's not even a curve. You come all the way up through 160,000 years of human history, and then all of a sudden, human population has just exploded, and we're going to be here at 8 billion here in year after next. So here we are. There's projections for the end of this century, Arctic being the warmest, but the whole world warmer. The place is changing, and I think we'll stop there. Climate, fascinating topic, and so many different things. Well, you know, I wish I had you all in class for the full semester so we could really dig into these topics one after another in depth. But I guess we'll stop here and hopefully maybe take a few questions. Thank you very much. What would we need to prepare in the case that we may be approaching another ice age? Well, you know, I was talking about the astronomical things about whether the Earth is nearing an ice age or going away from it. At the present time, the three variables that affect the amount of solar energy the Earth receives, two of them are making us colder. So from the pure secular reasoning, we're not seeing an ice advance from Mother Nature in the near time. And one of the things people like to consider now is, can we, if we continue our warming activities, can we so warm up the atmosphere that we would prevent another ice advance? I'm not talking science here. This isn't an answer. They're just talking about projecting forward. Are our activities something that would stop glaciers from advancing again? Don't know the answer to that. Boy, that's a good question. How will it take to melt all of Greenland? And as we used for the ice cube examples on the table, from your own eyesight, how slow these things are. And of course, the ice on Greenland's over a mile thick. So this isn't something we're going to see. Okay, I had Eugenia make a diagram there to show San Diego buried by melted Greenland ice, but that's not something we're going to see in our lifetimes or even in this century. We're talking centuries. But the significant point, the reason I was bringing that up was not that it's an immediate emergency. The emergency is if we pass the tipping point, then we couldn't stop it. That means we're passing on that flooding to future generations. Lots of fascinating background information, but hoping to hear about the context of San Diego soon. Well, thank you for the first part. And I'm going to take the second part as an advertisement for upcoming lectures. Because when we're talking about floods and we're talking about wildfires, then we're going to be seeing a lot more of what the changing climate means for San Diego. What is the highest temperature that people can survive under, and do you think we will reach that in our lifetime in various cities? Very interesting. The way we like to measure these things, we're so used to the thermometers that you're used to seeing. What we really like is what they call wet bulb temperatures, where you take that thermometer and you wrap it in a wet towel. What we're simulating there is not just the heat, but also the humidity. There's that old saying, it's not the heat, it's the humidity. Well, if we wrap the thermometer with a wet towel, meaning 100% humidity, then 95-degree temperature, it can be fatal to people in 6 hours. That's stunning. We're very used to 95-degree temperatures, but with lower humidity. Take those 95-degree temperatures, put it in 100% humidity, and even sitting in the shade of a tree, you could be dead in 6 hours. So, what parts of the world are liable to experience this first? Some of them are experiencing it now, but only for an hour or two. But those would be areas, think about over in the Middle East. Go up the Persian Gulf, some of those areas. Locally, where would it be most liable to be? Would be cities along the Gulf of California. I want to be near a warm water body to get the humidity level up. We already have the air temperature, but those are things that are coming. They exist now. They haven't quite reached the number of hours time to really make it a major problem yet, but that's going to be another thing that's going to cause migration. There's going to be areas that are simply basically unlivable unless you're living in air conditioning all day. And of course, you're warming up the atmosphere if you're doing that. Is the concept of tipping point problematic in that it defines a point in time, but not the scale of the time? Well, the whole thing is a problem, and the problem is that we don't know the scale of the time. We want to know where that point is, but we don't know the time scale. So that's part of the reason I try to emphasize tipping points for people to think about that. And this would be great if we can on some of those specific case histories I was talking about or showed on a diagram. If we could figure out where that point is, that would sure help planning. You could probably whip politicians into doing something, deciding something, if you actually knew where a tipping point was. Well, thank you for attending. I appreciate all these good questions. Next time we're going to talk about earthquakes, and the time after that, floods and wildfires, and we'll see a lot of influence of climatic effects in floods and wildfires. Thank you again for your interest.